I'll be presenting the basics of AI for PET image reconstruction. So AI and deep learning really can be regarded as software or code that learns from data or from experience rather than from a human explicitly programming the software. And so what we have then is typically code is a processing pipeline with input data and desired output. And we normally write code, for example, to process a sinogram in order to reconstruct an image. And I can depict that code as sequences of operators. And that's where we get the concept of deep from deep learning, where it's the idea of successive line after line, operator after operator code, basically. And the learning part is saying that we can train up what those lines of code need to be in order to arrive at the desired output. And this is useful when we know exactly what we want in terms of an output, but we do not know quite how to achieve the code for that output. And so when we've got a difficult task, such as identifying, for example, a kingfisher bird here as an input image, we don't know how to code up the necessary lines in order to identify that as a kingfisher. Whereas if we use these sequences of convolutional layers, these operators with nonlinearities in between them, what we can do is increasingly transform that input image into a different representation, into a feature map or latent space representation. And so deep learning networks really should be regarded, or one way of regarding them is as trainable or learnable code or programs. And this idea of line after line, in other words, increasing depth, is really what also allows a hierarchy to be formed and an increasing level of complexity to be obtained as we progress through each of those layers. Basically, we're increasing the contextualization and the level of abstraction of the information in that input data. Okay, so let's see then how we can apply the power of AI and deep learning to PET image reconstruction. So first of all, what is PET image reconstruction? Well, we've got, for example, a radio tracer distribution inside the brain here, inside a PET scanner, and we get measured data in the form of normally about 1,000 or more sinograms. The PET scanner can be modeled by known physics and statistics, the Poisson noise model, radon transform, Compton scatter, attenuation, and so on. And there I'm depicting the line integrals of the radon transform. And then what we're trying to do in reconstruction is to achieve some kind of inversion of the physics of the imaging system whilst accounting for the noise model, Poisson statistics, as well as ideally recovering lost resolution, for example, due to positron range. So where are we up to with PET image reconstruction? First of all, there are methods like filtered back projection, which used a Gaussian noise model. It's a least squares method. Then we moved on in the 1990s to considering the Poisson noise model, and that reduced the noise in the image. Then we improved physics modeling by positron range modeling, PSF, for example, with OSEM. And then more recently, there have been methods that include MR information to assist in regularization or reduction of noise in the PET images. And of course, we're vulnerable to noise when we have short duration scans or low dose injections. But none of these methods, this is a very quick summary of where we're up to with PET reconstruction, none of these make use of learning from data. So in other words, they don't make use of the AI paradigm. Okay, so let's look then at how we can begin to put AI into PET image reconstruction. So here then is an understanding of filtered back projection as a deep network, because we've got a sequence of lines of code. Conventionally then what we do is we filter each of the rows of the sinogram and then back project. Okay, so that filtering can be understood as a convolution of each row of the projection of the sinogram, followed by a physics back projection operator. And in fact, this is what was done way back in 1991 by Floyd. This publication was in Transactions Medical Imaging. And what he did was take that concept of filter back projection, but then decided to learn what that convolution kernel needs to be in order to go from a sinogram to a single point source. So he used one pair of training data examples, a known input and a desired output, in order to find the one single kernel that will be able to convolve each projection row such that when back projected will give the desired image. So deep learning, or if you like here even machine learning, just one single kernel, has been done for emission tomography from many years back. And this is a visualization of the kernel that he learned, and in fact it's very similar to the analytic filtered back projection kernel. It's just that here in principle you could also account for noise in the sinogram and so have noise compensation learned as well. Okay, so filtered back projection then can be regarded as a mapping of noisy measured data, which I'll represent along this axis, mapping to reconstructed images theta on this axis, and here in fact it's a whole if you like, a manifold of possible images that we could obtain. And what I'm representing here is the fact that the data can be noisy. We're using a Gaussian noise model with filtered back projection. It's a direct least squares estimate. And the linear operator that is filtered back projection is basically doing that convolution and back projection to achieve the inverse of the radon transform. And because it's using a Gaussian noise model and a very simple inverse of the radon transform, we've got a broad range of images that could be obtained. We could have very noisy data here, and we could get a very noisy reconstruction anywhere in this huge space of possibilities. Now, if we begin to build in that training, such as the example we looked at with Floyd, if I then started to include noise in the sinogram and yet still require it to be a perfect point source, then I can train up the convolution kernel and actually decrease the size of the possibilities of the PET images that we'll be reconstructing. So here, just using one training data pair, we can very likely improve the kind of images that we would obtain, even with a very simple learning process. And so here we're combining the physics and maths, so basically the direct least squares estimate, the inverse radon transform, with machine learning, with one training pair, one known input output pair for supervised learning. And in fact, this then could be taken to extremes whereby we completely remove the physics and just now rely entirely on example training pairs. Here I'm just showing 3, but if we were to go completely just to data and ignore physics, we could need hundreds of thousands of examples. And then what we'll be doing is linking sinograms with known ground truths by simulation, and that's done by DeepPET, as we'll see in a moment, or we could use very high count acquisitions. And so we can do the supervised learning where we're trying to map sinograms through this learned mapping to deliver something that reconstructions that match closely in terms of mean square error with the ground truth images. Okay, now typically the way we do this mapping then would be a little bit like that Kingfisher example I showed at the beginning, where what we do is we take the data and then we encode it through use of convolutional kernels, many convolutional kernels here per layer with many channels as well. And we also include nonlinearities in order to arrive at this kind of abstract latent space representation of the information in that sinogram. Once we're in that latent space, we can then decode that information again through convolutional layers, going from the latent space with limited spatial dimensions, but many, many feature channels here, all the way back to an image representation of the same information that was in that sinogram data. And here then we have examples of what really are convolutional neural networks, or CNNs, where we use these convolutional layers stacked in order to provide a mapping, a transformation from one domain to another domain. And the key here is that we can get away with far fewer parameters with these convolutional mappings compared to what the actual linear mapping would be to go from one domain to the other. And we'll see that in a moment. The point being, when we've trained these parameters for these convolutional layers, we can then put in test time data, a new acquisition of a sinogram, and then infer what the ground truth distribution was. And of course, the point is the mapping accounts for the noise as well in these data sets. So this is what was done with DeepPET. They trained an encoder and a decoder, a convolutional encoder, convolutional decoder, in order to take sinograms here, these are a certain dimension here, just 2D sinograms, to re-express that information in the form of an image. And the point to note here is that they had to use 200,000 simulated training data pairs, simulated because you need to know what the ground truth is for a given sinogram, in order to learn the 60 million parameters, mainly for all these convolutional kernels in all of these layers. And they trained them such that the output matched the ground truth in terms of minimizing the square error between the two. And as alluded to before, had this been a pure, simple linear mapping, we would have needed 1 billion parameters or more to do that mapping, and we wouldn't even have the symmetry benefits of what convolution offers to us. The results of that method are quite convincing with simulated data. Here we see the ground truth here, filtered back projection here, iterative reconstruction here using a Poisson noise model, so doing better than filtered back projection, but using their data-based DeepPET architecture, they get very impressive results. With real data, not quite as impressive. Here, simulation again showing improvements in structural similarity of DeepPET compared to iterative reconstruction, and certainly better than filtered back projection. And of course, these architectures are very fast to run, take a long time to train, but much faster at inference time at the reconstruction stage. There was more work done on DeepPET by Zanli Hu et al. In 2021. They added a discriminator to the loss function for training that DeepPET architecture, as well as a perceptual loss. I don't have time to go into details of these concepts here, but basically changing the loss function, the way of assessing the output of the architectures and the level of agreement with the ground truth by improving that loss function. You can see they go from the DeepPET result here, this is the ground truth here, there's the EM reconstruction. They go from that result there and they get some measure of improvement. If you compare to the ground truth, this network with perceptual loss and a discriminator does do better, and the metrics for structural similarity and signal-to-noise ratio bear that out as well. So in summary then, we've looked at examples of direct architectures for PET image reconstruction, DeepPET, DPIR-Net as well, and also AutoMap could be included, but I haven't had time to cover that for MR reconstruction. They use few modeling assumptions other than the expressivity, the inductive prior or inductive bias of the network itself, and they are very fast to run. But of course, they need a lot of training data. They've lost our knowledge of the physics, the Poisson noise model, and they have many parameters, although fewer than what a linear mapping would be, but still a large number of parameters. And up to date, really, they've only been practical for 2D reconstruction. So what we really need then are 3D capable reconstructions that use our physics and also make use of that learning paradigm as well. So that's where we'll go on to iterative reconstruction. And what we'll be doing here is embedding deep learning into iterative reconstruction. Well, why do that? Well, iterative reconstruction is well known as better than filtered back projection because it allows better modeling of the physics, the accurate system model, and more accurate noise modeling. So the goal here then will be to use that physics knowledge and combine it with that machine learning, data-based learning as well. And we want it to be practical for 3D and only get by with limited number of training examples. So there are convolutional neural networks that are used for this. I list some of the references here, and I'll be focusing on the example that I worked on with Abulfaz Moranian a few years back. And so this is the improved physics modeling of iterative reconstruction. You may recall before we just had a radon transform under consideration for inversion, for filtered back projection. But here what we can do with iterative reconstruction is easily build in a kernel to model positron range, and then we can build in the radon transform, for example, if we trust that for the geometric model, and then we can build in attenuation, normalization, build in scatter and randoms, and end up with quite a sophisticated model of the physics of the acquisition process. So iterative reconstruction makes use of that more advanced physics modeling, and builds it into an expectation maximization update, which maximizes the Poisson log likelihood. I don't have time to cover those principles here, but all you need to understand is that we start off with an initial image and it goes through a very simple forward projection, ratio, back projection and multiplication many times to deliver some output image. And so this is like a cascade of operations that is nothing more than something like a deep network. And so what we'll be doing is building deep learning into that. Now, if we have noisy data, should be no surprise, we get noisy reconstructions. And this here is known as unrolling an iterative reconstruction because we've explicitly shown many different updates here. And this concept was really by Gregor and LeCun from 2010, the idea of unrolling iterative methodologies. And so with noisy data, we get noisy reconstructions. What do we do about that? Well, conventionally, we do maximum a posteriori EM reconstruction, where we build in a denoising component with that EM update that we've just been touching on, fuse them together to get an improved reconstruction. But this uses what's known as a quadratic prior, and that's unlikely to be optimal. It's mathematically convenient. We can do better by building in MR information into the denoising step, combining that with the data-based EM update step to get improved image quality as shown here. So this is based on guidance weights using the Bauscher method. And you can see here we've got quite a good improvement in image quality. But again, how much can we rely on that? It's unlikely to be optimal the way we do that smoothing. And we don't even know how much attention to pay to that MR information. And this is where deep learning can really help. So what do we do with an unrolled iterative reconstruction that uses deep learning? Well, we take this kind of EM type cascade of operations with the denoising for MapEM. And what we do is build in a convolutional neural network, which is this operator here, this Fn, operating on a given image X in this series of updates. And here then, for 2 minutes, so it was very noisy sinogram data, we get a certain reconstruction. Here I've showed an artificially good one from the previous slide, but in general this is going to be a very poor quality image. So what we'll do here is look at using high quality reference data, for example 30 minutes, 15 times longer acquisition to get a high quality image. And then what we'll do is train up using mean square error loss here, the convolutional neural network, which is in each one of these modules. Here I'm showing 1 to n modules, and we can either use the same network or a different network in each module, train it up such that the output here matches a high quality reference. So making use of that machine learning paradigm. If we do that, this is the spelling out of the architecture for the CNN. Again, it's just that cascade of operations with the database update using the MR information as well. We can get quite an improvement in image quality. This, though, only needs 77,000 training parameters, not the much larger network we saw before with DeepPET, and only 35 training pairs, nowhere near the huge number required for DeepPET. Results are very convincing. This is a reference data set for 30 minutes, conventional OSEM, and then that unrolled architecture with the CNN built in gives very good results with good comparison to the reference data. This is real FDG PET data from the simultaneous PET-MR scanner. Okay, so in summary then, we've looked at how to unroll iterative reconstruction and build in deep learning into those unrolled reconstructions. It uses all of our physics and statistics knowledge. Much reduced parameters are involved, hardly any training sets are needed. And this now is practical for 3D reconstruction, and we'd expect improved generalization by making use of our known physics and statistics and not just entirely relying on data like DeepPET. But it is slower than direct reconstruction. So recent directions could be of interest. Deep kernel representation can work on a time sequence of images, and what it can do is generate feature maps from a time series of images and then use those feature maps here in order to generate a matrix of basis functions. So what we're doing here, this is the impressive work of Siqi Li and Guobo Wang, quite recent. What they did was basically learn how to derive the best kind of features for a given image in order to then use those features in a comparison matrix for building spatial basis functions, which are then used in conventional EM type reconstruction. If they do that, then they get quite impressive results. This is conventional MLEM. This is a conventional kernel method that just looks at, for example, time activity curves to establish the feature vectors, and then their learned kernels, their learned feature vectors for the kernels deliver very improved results for merely 2-second timeframes in dynamic imaging, and those improvements bear out as well if we look at noise for a given region of interest mean for real data. So their method here is much lower noise compared to conventional MLEM. Just to finish, total body PET also now is making use of deep learning. Here we've got the recent work showing mapping from an SUV image for total body PET all the way through to kinetic parameter Ki for FDG imaging, just by using this kind of cascaded UNet type architecture. So in summary, outlook, how are we going to adopt this kind of advance? Well, there is a risk of artificial features that could be cropping up in these images that could concern people. I would suggest using low complexity networks will reduce that risk. Or indeed, we could just use AI to select noise compensation level or how much anatomical guidance to use if we want to use MR guidance. But I think where we really need to go is Bayesian deep learning, where we express the uncertainty within each one of our medical images. And of course, the ideal, as talked about, is to use our knowledge of physics and maths and stats with the manifold learning ability of AI. And then finally, we're going to need clinical assessments of the reconstructed images, ideally with benchmark data sets. So thank you very much for listening. Far more information is available in these publications. Thank you.